In the last session, we discussed about lap winding, and we saw how in the lap winding, the coil sides of a same coil are connected to two adjacent commutator segments, and you can either have a progressive lap winding or you can have a retrogressive lap winding. As in opposed to this, in the case of a wave winding, what we do is as in opposed to this, in case of a wave winding, if this represents your coil sides, if this represents your commutator segment, sorry, and what happens is if coil is connected, if one side of a coil is connected to commutator segment 1, another side of this coil will be connected to some another commutator segment, say for example 5. Fine. The second coil will start from commutator segment 2 and end up at commutator segment 6. Third coil will start from commutator segment 3 and end up at commutator segment 7. So there is a difference of 5 minus 1, that's 4 commutator segments between the two coil sides of coil 1. Fine. So if this is your coil 1, and YF represents the commutator pitch, that actually this tells us to which two commutator segments are the two coil sides of a coil connected. In case of lap winding, we saw this commutator pitch is equal to 1, but in case of wave winding, how we can basically calculate commutator pitch? For that we have a formula 2C plus minus 1 divided by P, where C is the number of coils and P is the number of poles. So for C equal to 9, P equal to 2, YF will be equal to, taking plus 1, YF will be equal to 10, and for C equal to 9, P equal to 4, YF will be equal to 5. Fine. So accordingly we can decide what will be the commutator pitch, and accordingly the coils will be connected to different commutator segments. So this is the case of wave winding. So in this case, the coils look like progressing in a wave fashion and therefore are known as wave winding rather than a lap winding. So this is the case of a wave winding. So if we take a look at this diagram, this is again the same what has already been discussed. You can see coil 1 in this case being connected to commutator segment A and commutator segment F, coil 2 being connected to commutator segment B and commutator segment G. So if there are 9 coils, accordingly YF can be decided, the commutator pitch will be decided. That we just found out it's actually 5 for P equal to 4. Fine. Now what was important in the last session was we discussed the number of parallel paths in a lap winding. So number of parallel paths for current to flow is equal to number of poles for a lap winding. Let's take a look at how this how this will look in case of a wave winding. What will be the number of parallel paths that will be produced for the current to flow in case of a wave winding. For that, let us have this. Let us take a case of a 4-pole DC machine as shown here. This is a 4-pole DC machine and it has 18 slots. So that means there will be 4.5 slots under one pole at a time. So at any time we can assume that 5 poles will be under the north pole, 5 will be under the south pole. So let us assume what we'll be doing is we will assume that these sets of slots are under the influence of South Pole, these slots are under the influence of North Pole, these again here are, these are under the influence of South Pole, and these are under the influence of South Pole. Since the number of poles are not uh, equal, they are not fitting with the number of uh, we do not have equal number of poles and equal number of slots under every pole face at a time because of the nature of because of the number of slots. To make things easier, let's take an example let's take a different example, or let's continue with this example. And since this armature is rotating, so the number of slots can be anywhere at any given time. I'm assuming my south is here right now for this particular case. My north is influencing these number of slots, my south is influencing these number of slots, and the north is influencing these number of slots. Fine. uh, so if south so accordingly I can set the direction of current for these conductors lying under the south pole as cross, that means into the coil. Fine. Again, for these conductors it will be cross, that means into the conductor. For these slots it will be dot, that means out of the conductor. And for these slots it will be again out of the conductor. So I have 5 slots at this time under the south pole, 5 slots under the influence of north pole, 4 then under south, and 4 under north. Instead of assuming 4.5, I'm assuming complete integer under one pole at a time. So accordingly I can say accordingly if this is into the conductor, that means the direction of current will be like this, like this, like this, and like this, and like this. Fine. So out of the conductor means current will be like this, like this, like this, and like this, and this is again out, so this means like this. In means like this, in means like this, in out, conductor, current is out, current is out, current is out. Fine. So now let's have a look at each and every commutator segment. So you can see at this commutator segment A, the two coil sides that are connected, the current is moving out from both sides. At commutator segment B, current is moving in from one end, out from another end. At C, current is moving in and out. D, current is moving in and out. E, current is moving in and out. F, current is moving in and out. G, current is moving in and out. At H, you have two coils that from which current is moving in from both sides. I, it's moving in and out again. So in case of a wave wound DC machine, what you have seen, there are only two commutator segments even for a 4-pole machine, where the direction of current is in from one at one commutator end and out at another commutator end. That means only two parallel paths for current are produced in this case. So if you have different coils that are attached here, so in this case only two parallel paths are produced. That means A is equal to 2 for even case of a 4-pole machine. Even if you take a 6-pole machine, you will see that A is equal to 2 number of parallel paths. Fine. So why this is important? Because we have actually calculated voltage in one coil side equal to BLV. Fine. Then if there are z number of coil sides or z number of conductors on one end, so that means not Z. If there are n number of conductors on this side, that means n BLV will be the total induced voltage. But we know what we have derived the formula for Z, that is the total number of conductors. So Z for this case will be equal to n divided by 2. Z for this case will be 2n, that means n is equal to Z divided by 2. So this Z divided by 2 will be substituted here to calculate the total EMF induced in this case. For a lap wound machine, what we saw, the number of parallel paths is equal to the number of poles. Therefore we deduce that EMF will be equal to Z divided by A into VBL. But in this case A is equal to 2 for all the cases, so it is equal to Z divided by 2 into VBL. Fine. Now we have already established we can represent V in terms of R omega and B in terms of phi and area. So accordingly we can deduce the total EMF induced in case of a DC machine for a lap wound case as well as for a wave wound case. Now we need to understand that for a lap wound case, A will be equal to 2 and wave wound case A will be equal to 2, and for a lap wound case A will be equal to P. Fine. Also we have deduced the formula for Z, that is the total number of conductors, in the last session. I told you that one coil side basically represents one conductor. Z means one conductor. It actually represents one conductor. So each coil will have actually two conductors, and if you have C coils and n number of turns per coil, so the total number of conductors will be 2nC. Fine. NC, where NC represents the number of turns per coil and C represents the total number of coils. And EMF equation accordingly can be established as Z divided by A, because in one parallel path, if Z is the total number of conductors in one parallel path, then total number of conductors will be equal to Z divided by A into BLV. Fine. Now we can actually represent V all in terms of R omega and B in terms of phi by A. So therefore this becomes equal to phi Z and P divided by 60A. I have done actually one more thing here. Instead of writing omega, that's in terms of radians per second, I have written in terms of N in terms of RPM, and you can find out in terms of RPM what will be your total induced, what will be your formula for omegas. Fine. So the pi goes away, omega goes away, you are left with N divided by 60. Fine. Now A will be 2 for a wave wound machine, and for a lap wound machine this A will be equal to P. So this finishes our discussion of wave winding and lap winding. We will continue with the equations we'll actually start with some examples on the EMF equation in the next session.